Alright, we talked about choosing learning rate schedulers and choosing optimization algorithms. Let's now talk about choosing activation functions. And yeah, we can consider the hidden layer activation function as yet another tuning option for our multi-layer neural network training. So as you recall, we placed the activation function just behind the linear layers, the fully connected layers. And yeah, in fact, there are many activation functions out there, and you may wonder how we choose a good activation function. Well, the boring news is that there is actually no universally best activation function. Across different problems, as you can see here on the slide, different activation functions perform differently. There are some activation functions that are better sometimes than others, but usually universally, there is no best activation function. So I'm not going to talk through all these plots here, but if you are interested, I invite you to pause the video and inspect these more closely. So maybe let's talk about the most common choices of activation functions, at least those that most researchers and I personally prefer in practice. We will start with an activation function that we have already seen in previous lectures. And that is the logistic sigmoid function. It's in fact the very first activation function we introduced when we talked about logistic regression. And just for reference again, so you see where it's placed in the code, like other activation functions, the sigmoid activation function is usually placed just directly after the fully connected layer. And even though the sigmoid activation function is very intuitive and popular, it's actually not a very highly recommended choice for the hidden layer activations. And that is because it is actually bad for convergence. It will slow our training down. So why is that? Why is the sigmoid activation actually not recommended for the hidden layer activations? So to understand the issue here, we have to look at the derivative of the sigmoid activation function. And it turns out the derivative of the sigmoid activation function is itself times 1 minus itself. So let's look at the extremes first. If we have a very high net input value here on the x-axis, what will happen is that the sigmoid activation will near 1.0. And if we have a sigmoid activation value of 1.0, the derivative 1 times 0 minus 1 is actually 0. So we have a derivative of 0 here in this case. Vice versa, if we have a small net input value, or that means a very negative net input value, that means that the sigmoid activation will output is 0. And 0 times 1 minus 0 is 0. So in this case, our derivative will also be 0. So the largest value we can actually get for the derivative here is when the net input is 0. So if the net input is 0, the returned value by the sigmoid activation function will be 0.5. And 0.5 times 1 minus 0.5 is equal to 0.25. And 0.25 is the largest derivative that we can get from the logistic sigmoid activation function. So in this plot now I'm showing you the sigmoid activation function in blue and the derivative function here in orange side by side. Yeah, and you can see the largest value here is at 0.25. Now the reason why the logistic sigmoid function is not a good choice for the hidden layer activations is that the largest sigmoid derivative is 0.25. And if we have a 0.25 here, if you think about multiplying it by the different terms in the backpropagation algorithm, then we will actually have the issue that we are degrading the error signal. So the more layers we have in our network, the hidden layers with sigmoid activation functions, the more we degrade the error signal, because at most we multiply a value by 0.25. And multiplying a value multiple times by a small value, smaller than 1, will degrade the signal. And this will slow down the training and slow down the convergence when we compute the gradients. And yeah, that's the reason why we don't use the sigmoid activation function for our hidden layers. Now let's talk about another commonly used activation function that we have already encountered earlier. And yes, that's the relu activation function, the rectified linear unit. So in contrast to the logistic sigmoid activation function, if we have a net input value that is positive, we will have a derivative of 1 when we are using the relu function. And otherwise the derivative is 0. So if we have negative net input values, at that unit we won't update because we have a multiplication by 0 when we compute the gradients. On the other hand, in this chain rule that we apply during backpropagation, we have a multiplication by 1 if the net input is positive. So in this case, we don't degrade the error signal. And that's one of the reasons why relu is actually a commonly used activation function in practice, because it helps the network to train faster than with a sigmoid activation function. So relu is a very popular, simple and robust choice as a hidden layer activation function. And yeah, as we have already seen, it's also very easy to use the relu function in PyTorch. Now, while the relu function is a simple and popular choice, let's also talk about the latest trends here a bit. So in recent research papers, 3 other activation functions are also commonly used now. That's the gelu function, swish, and mish. So yeah, here I plotted these activation functions side by side, and as you can see, the overall shape is very similar to relu, where it's flat on the left-hand side and relatively steep on the right-hand side. But yeah, coming back to the original question, which activation function should we use in practice? Unfortunately, like we said earlier, there is no right solution. It all comes down to trying it out in practice and seeing what works. So I invite you to experiment with these different activation functions and see if it makes a difference in your neural network training. And if you do that, I will guarantee you that you will find that the previous network that we used in the coding sections will be really hard to train with a sigmoid activation function. And I bet that relu and, for example, gelu will result in almost identical performance when you swap them. So in this video we talked about the different options for the activation functions, and we said that choosing an activation function is essentially a hyperparameter or a tuning process. We will in the next video talk about how we can automate this hyperparameter tuning process.